Okay, in this video we're going to look at what it means to be a continuous function. Think about what it means or what could break a function from being continuous, and so we call all of that continuity. Alright, so I've got this piecewise function from the other day and I've got a question: is f of x continuous at -2? So look at -2 and ask yourself, what do you think? A -2, does it look like it's a nice continuous graph? At that value, looks like it to me. So yes. Okay, so it's continuous at this point. So question 2, if a function is continuous at a point, does that mean that the limit must exist at that point? If no, or if not, give an example. Okay, so if a function is continuous at a point, does that mean the limit must exist? Well, let's use this as an example. So we just said it's continuous there. So does its limit exist there? Is it from the left and from the right, do we get the same number? So the left-hand limit looks like it comes out to be 2, and the right-hand limit looks like it also comes out to be 2. So it appears that this limit does exist. So go ahead and pause the video. Just because that's a yes doesn't mean that there's not an example where that would work. Pause the video and see if you can come up with a counter example. Alright, so that one is, if a function is continuous at a point, does it mean that the limit exists at this point? Yes. There's no counter example to that. If it's continuous, the limit exists. Alright, what about at x equals 2? So look where x equals 2 and ask yourself if it's continuous there. Alright, I would probably call that a no, or not probably, I would. Because this is an open circle. At that instant, for some reason, it jumped all the way down here. So if there's some kind of break in the graph, it's not a nice, smooth, continuous graph, then it's not continuous. Alright, so the follow-up question to that is, if the limit exists at a point, does that mean it's continuous at that point? So that's the opposite of what this said. This said, if it's continuous, does the limit exist? And now it's saying, if the limit exists, does that mean it's continuous? So go ahead and pause the video, think about it, commit to an answer, and see if yours matches up with mine. Alright, so on this one, I would say no. I mean, this is a great example right here. The limit exists. The limit, flip this around, the limit as x approaches 2 for, what was this, f of x? Well, the limit from the left was 2 and the limit from the right was 2, so it certainly exists, 2 exists, but it wasn't continuous. So if it's continuous, the limit exists. If it is, the limit exists, it doesn't necessarily mean that it's continuous. So the keywords in there are must be. Could be continuous, but not necessarily must be. Alright, if a function is continuous at a point, must the function be defined at that point? Why or why not? Okay, so again, think about that question, pause the video, see what you come up with, and then come back. Okay, so if a function is continuous at that point, must the function be defined at that point? So, I don't know, if I tried to sketch something, and I think about some value like a, this is definitely continuous at a, well, I had to hit that point. But let's say I didn't hit that point. Let's say the point's here, but the rest of the function is doing something like that. So now at a, it doesn't appear to be continuous to me. It looks like the limit exists. The limit from the left is equal to the limit to the right. but that point, it's got to fit in that spot there. So if it's not, then it's not going to work out. So if it's continuous, which that picture was not, must the function be defined at that point? And then we would say yes. To explain why, it would be a break in the graph. So if the function is not defined there, then it would be a break in the graph. And if your graph is breaking is not really a mathematical term, but if your graph's breaking, it's not continuous, or we would say discontinuous. All right, so back to the graph. Is f of x continuous at 1? So here's 1. So to me, looks like it is not continuous at 1. For some reason, the limit exists, but for some reason it bounced up there, so it's not continuous. There's a break in the graph. So if a function is defined at the point, must the function be continuous at that point? Well, what you need to see here is that f of 1 is 2, so that means it exists. But just because that exists does not mean, so no, doesn't mean that it has to be continuous. Okay, and we can see that right here. F of 1 exists, but because it's not in the right spot here, if it fit in right there, it would be continuous, but it didn't. So it's got to be like in the right spot. So I would say it's something like f of a must be in the right spot. Okay, and we'll say that more mathematically here in just a minute. Alright, so now this is kind of beating around the bush here, where it's trying to hint at some of the stuff required to be continuous without just flat out coming out and saying these are the requirements to be continuous. But look at what we talked about in 1 through 7. Think about when is a graph continuous, when is it not continuous, what conditions have to be true, what conditions don't have to be true. And use that information, determine what things must be true in order for it to be continuous. And I give you a hint. There's 3 things I'm looking for here. So pause the video for several minutes here and see if you can come up with some or all 3 of those. Okay, so one of the, I guess the order doesn't really matter here, but one of the things that has to be going on here is that the limit as x approaches some number, we'll just say a generic number a, it has to exist. So that means whether you come from the left or whether you come from the right, those need to be the same value. So think about what happens if those are not the same value. Like, let's say I was talking about 1. Well, if to the left of it, it approaches -2, and then to the right of it, it approaches +2, that's obviously a big break in the graph. That's discontinuous. We need the limit from the left to equal the limit from the right. We need those values to be coming towards the same y value for whatever value you're talking about, value of a. Okay, so there's one thing that has to happen. From one of these examples, it hopefully helped you see that that value has to exist. So whatever value I'm trying to find a must exist. And so a visual of that would be like something like this, and I'll call this the a. So sure, the limit works. So my condition 1 is fine here. From the left and from the right, they're approaching the same number. But if this doesn't exist at all, if there's no y value at an x value of a, then it's skipping that point, it's skipping that instant, and if it's skipping that instant, then it's not continuous. I would suggest that you go ahead and make these kind of sketches too. I'm just removing them to give myself a little more space. All right, and then finally this last one, which I kind of purposely didn't try to say very mathematically, but for f of a to be in the right spot, well, what is the right spot? So over here, I talked about, this, it was missing this one, which made it discontinuous, but it existed way down here, which just didn't fit. But if you moved it up here, then it would be continuous at 2. So this condition was being met. The left and the right are the same. F of a, it existed, so that condition was being met. But the one thing that didn't make it work for f of 2, or as x approaches 2, is that the limit even though it existed, it was approaching 2, but f of a was at -3. And for it to be in the right spot, you need those to be equal. So it's not enough that this point exists. It needs to exist equal to what those limits are trying to approach to. It's got to be a perfect little fit. All right, so to prove continuity, and you will be asked to do that, either in class, quiz, test, AP test, you will need to be ready to say, here are the 3 things that I know, or I can prove that something is continuous because these 3 things are being met. So the limit from the left of a function has to equal the limit from the right. So you would need to state and show that that was true. There's got to be a point there. Otherwise, there's a hole there. And if there's a hole there or an asymptote there, then there's a break in the graph. And finally, not only does it have to exist, but it needs to be equal to what the graph is approaching. It needs to fit in there just perfectly. Okay, so I guess I don't have to write that. I can just do this. This implies all of that. So those are the 3 ways, 3 things that you must state to prove continuity. All right, so now let's look at some examples of those being broken. So I've kind of said those on the other things, but I want to make sure I state those again because sure, you can memorize all 3 of those, but I think it's more likely to stick if you make up examples where they're not being met. Okay. All right, so we've got, let's make a condition where the left and the right are not the same. So from the left, let's say it's approaching 1. And then from the right, let's say it's approaching 3. Okay, so maybe it doesn't exist here, it does exist there, doesn't matter. But you can see that's a big break in the graph. The limit from the left doesn't equal the limit from the right, so that's why this guy is necessary. That helps make sure that they're kind of lined up. It's not jumping up here. Okay, f of a must exist. So if here's a, and here's my graph, but at that instant it doesn't exist, then there's a break in that graph. So if you've got an instant where the graph doesn't exist, and that instant is what you're trying to test for continuity, then it must be there. Okay, and then finally these have to fit, because if they didn't, so let's say f of a exists, but it's way up here, and the limit approaches, I don't know, 2 from the left, and the limit approaches 2 from the right. But at that instant, these aren't equal. If the limit doesn't equal the point, if this doesn't fit in there, then it's not continuous. You can see that jump, that instantaneous jump there, messes up. So that's why this requirement is needed. If you've got all 3 of those things happening, then it has to be continuous. All right, so there you can see now that there's different types of discontinuity, and you will need to be able to classify them and say what types is going on here. So using this graph, we're going to talk about jump discontinuity, and jump discontinuity is where you've got a break in the graph and it looks like it's jumping. So to me, like, well, let's do these in different colors. How about x equals 1? It's the graph just in one instant completely jumps from a y value of 1 to a y value of almost 5. So that jump makes it discontinuous. So x equals 1 and is an example of jump discontinuity. Okay, there's another example of jump discontinuity. So if you would go ahead and write in where you think that is. Okay, and it looks like x equals 2. Looks like it's jumping at that instant. So those would be the two examples of jump discontinuity. That one's usually pretty easy for people to remember because it looks like a jump. All right, also one that's not too bad to remember is infinite discontinuity. And that's when your graph goes to infinity or negative infinity, so like an asymptote. So this is certainly a break in the graph, and it's happening at x equals 4. So when it goes to infinity, positive infinity, negative infinity, or both, you're getting an infinite discontinuity. That's that type of break in the graph. So that's the only one for that one. And then removable, this is like when you have, you should probably put in parentheses here. This is like when you have a hole in the graph. And the graph didn't show up great. Maybe if you can zoom in on your digital copy, but there's supposed to be a hole right here. So if there's a hole right there, it doesn't exist, then there's a break in the graph there. So x equals negative 2. So these two people don't usually struggle with. This one, sometimes people forget that this is for a hole, but we call it removable discontinuity. And it could also be like, you know, the point could be up there. So, but that's still removable. All right, and then a pretty uncommon one, but I wanted you to see it. If a graph goes back and forth very, very quickly, if it's oscillating like this, in this example, at x equals 0, it actually doesn't, it's not continuous either. It kind of breaks at that point. So if you want to try to graph that in your calculator and zoom in a little bit better, you can see, you might be able to see a little bit more. But when it oscillates back and forth and it has a break at a point, that's referred to as oscillating discontinuity. Not very common though. All right, so let's actually use some piecewise functions and do some limit questions, and then we'll think about if it's continuous or not. And if it is, we're going to say which of the three conditions are being met and which ones are not being met. All right, so I would say one thing that students are going to struggle on here is you don't practice graphing piecewise functions enough, unfortunately. But you should be able to graph y equals negative x squared. But then only keep the part where x is equal to, solid circle, or less than 0. So I actually don't want this piece. And, okay, so this was this piece. But then also graph y equals x. So y equals x looks like this. But only keep the x values greater than 0. So that would be this. And an open circle there because it's not including that one. And you put those two pieces together and you end up with your piecewise function. I want to fix this one. Try to make it look a tiny bit better. Okay, so now that we've got it graphed, we can say, well, the limit from the left of 0 appears to be approaching a y value of 0. From the right of 0, it approaches 0. And since the left and the right are equal, then the limit is 0. And so is it continuous there? Well, since I have a visual, it's easy for me to say yes. And which of the three conditions of continuity are being met? Well, if it's continuous, then all three. So I would need to say the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right. It's condition 1. F of 0 exists. That's condition 2. And f of 0 is the same thing as the limit as x approaches 0. The limit was 0, and f of 0 is 0. So those are the 3 conditions. Now, I know it seems like a lot of work to write all those out, but you really need to do that, because if you don't practice writing out those conditions, you're not going to know them. Okay, so I'm asking you to do the same thing on 17. So on this time, why don't you pause the video, give it a shot, and once you get stuck, unpause the video and I'll help finish it for you. Alright, so to graph it, the top graph is going to be the square root of x graph, shifted right 1. 5, 2. So that would look like that. And I'm only keeping x values that are greater than or equal to 1. So equal to 1 is a solid circle, greater than is all of that. Then for the bottom half, that's like mx plus b. So a y-intercept of -2 and a slope of -1. So it's going to look like that. But only keep the x values less than 0. So or less than 1. So don't include 1 and don't include anything bigger than 1. Okay. So one hint, if your graph doesn't look right, this is a function, piecewise function, and remember, functions have to pass the vertical line test. So if yours isn't passing the vertical line test, you don't really have a function. Alright, now that I've got that drawn, I'm looking at 1. The limit from the left appears to approach -3. From the right, it appears to approach a y value of 0. Since those are different, that does not exist. And is it continuous at 1? Well, no, of course. I can see this big break here, so no. And so what conditions are being met, if any? Obviously not all 3 are being met, otherwise it would be continuous. But the first one's not being met. The limit from the left is not equal to the limit from the right. I guess f of 1 exists. It's good that this value exists, but that's the only thing it's got going for it. This isn't in place of this, and the limit from the left is not equal to the limit from the right. It's forcing it to jump up. So there's only one condition being met. But the first condition, no, and the third condition, no. Alright, try again with 18. Go ahead and pause. And, well, on 18 I kept the numbers the same, so I forgot to change those, so never mind. You don't get any extra practice on that one. We'll just have to move on. Sorry about that. Alright, and then finish up, we need to find the values of a and b that make the piecewise functions continuous everywhere. So this is actually a pretty common type of question to show up on the AP test. Likewise, we like to give it to you so that you can practice it, but it's just not as easy as the past questions. I mean, I can graph this, I can think about limits, and if I have those memorized, I can tell you what works and what doesn't work. But in this is much more abstract. I'm trying to find values of a and b that make sure that these are continuous everywhere. So this top one is kind of ready to go. It is y equals x plus 1, so that's like mx plus b, y-intercept of 1, slope of 1, and I want to keep the x values less than 1. So don't include 1, but include everything less. So that's the top. Alright, I'll do the same thing for the bottom. Y equals 3x. Well, 3x is, it's also like mx plus b, it's just that b is 0, and it has a slope of 3. So up 3, right 1, 2, 3, up 3, right 1. It looks like this. Okay. So no judging my graph here. I know it doesn't look great. But I'd only keep the values where x is equal to 2, so all the way up here. and greater than 2. So that side, not this side. That bugs me too much. I gotta fix that a little bit. I'm not a 4, 5, 6. Okay. I'm not an art person, so. So to be continuous, I've got some other function, ax plus b, that's supposed to connect these because we want this to be continuous everywhere. So I've got an idea of what I want it to look like. I want it to exist here. I want the limit from the left and from the right to be the same here. I need these to connect. I need it to do something. I don't really care if it zigzags back and forth, but ultimately it's got to touch here so that the limit from the left and from the right are the same there. So what's happening is at x equals 1, I'm trying to make sure that not just x plus 1 gives me a value of 2, but I want to make sure that ax plus b gives me a value of 2. So I want those two to have the same y value. So I'm going to set those two equal to each other. And then up here, ax plus b is right here, this line in blue, and then this is 3x, and at that instant of 2 I want them to be equal. So I want 3x to be the same thing as ax plus b. But now let's think about when. I don't want these to always be equal. I don't want them to always have the same y values. I don't want these y values to be the same as these y values. I only want them to have the same y values when x equals 1. And for this one, I want them to have the same y values when x equals 2. That's like me trying to get these like Lego pieces to fit together. I want them to have the same y values, so it's going from this function, it hands it off at the right place to this function, and then hands it off to that function. Okay, well, let's go ahead and plug in a 1. Oops. Plug in a 1 for x. So this would be 1 plus 1 and a times 1 plus b. Well, I can't finish solving that. I can't solve for two variables with just one equation. Luckily, I have this guy, and I can plug in a 2 for him. Okay, but a times 2 would be 2a, and 3 times 2 would be 6. And so now I've got a system of equations. One equation in a and b, and then another equation with a and b. So a plus b is supposed to be 2, and also 2a plus b is supposed to be 6. So all the way back to your Algebra 1 days, solving system of equations, you can do elimination, substitution. When you got a calculator, you even learned matrices in Algebra 2 on how to deal with this. But you need to be able to deal with that any way that you want to, except without a calculator. So I'd probably just subtract this whole function. So a minus 2a, b minus b, and 2 minus 6. And then I did that because I saw my b's would cancel out and allow me to solve for a. And then once I know one answer, I can then substitute that into either equation. 2 times a, now that I know a is 4, plus b is supposed to be 6. So b must be negative 2. So there are the values of a and b that make sure that this is continuous everywhere. Now, to make sure that this makes sense visually, so you can see what's going on here, let's actually plug those in so that you can see that it works. This was supposed to be ax plus b, so 4x plus negative 2. So what would it look like if I graph that? So it would have a y-intercept of negative 2, and it would have a slope of 4, so up 1, 2, 3, 4 to go right 1. So it starts off where I want it to, and then it goes up 1, 2, 3, 4 to go right 1. So you can see those values of a They hand off perfectly here because I set them equal to each other for that x value, and then they hand off perfectly here because I set them equal to each other and plugged in at that x value. So now we're pretty confident in our answer. We can see that it's continuous everywhere because I made us a graph. But we don't always have a graph, but the same process is what you would want to try on your own. All right, so that concludes the notes for this video. Please, as always, go back and rewatch the parts that you struggle with the most, and then move on to the assignment I give to you.